renew the invitation so that I could at least come this year. So that's much appreciated, and it's also really turned out to be a really nice workshop, very interesting. So it's very happy that I made the long way in braving the jetpack. Right. So Jonathan actually in his talk actually had the title and said an apology, and sorry, louder? I'm closer to him. Okay. Okay, sorry. I have to get used to that. Okay, I'm so sorry. So Jonathan in his talk did have the addition an apology, and maybe I should have put this also because this is not really going to be about resource theories. We're not solving these problems with the resource theories, although probably one should. It would be much nicer, but we did it without that we managed somehow, although we will discuss this at the end. Okay, so this is about some problem that's actually working around with us, at least we started about 4 years ago or something like that. And we just put it out on the archive now. And so this is work of PhD, first work from his PhD from Raphael Weber, who suffered through this during his master's already and then carried on. Yeah, so it was really a heroic effort of his. Okay, so
oh, I don't think the clicker works. It's not connected to anything. It's just for. It
was working.
Was that?
Oh. Yes, it was. It was. Let's see.
If you could click on the screen to go back into everything.
The meeting is recorded. Okay, so I can climb down again. Sorry. Okay, so this is about heat engines, and okay, we all know heat engines from thermodynamics up there. It's a Carnot engine, so you put it in touch with some heat paths, you let it expand, do some work, and then all sorts of things. And we can work out the efficiency of that machine using the second law of thermodynamics, is 1 minus Tc over Th. And that is true when the machine is, well, quasi-static, really, very close to equilibrium and can thermalize in peace and quite perfectly and all these sort of things. So it's highly idealized. And in a sense, it's actually really, it's almost static. And that's why we can also achieve then the Carnot efficiency at the end. So that's fine, that's wonderful. But real world machines are slightly different. So when you, for example, go to various heat engines and nuclear reactor and a coal plant and so on, and then you see here the Carnot efficiency, you can work that out, 64%, 48, 32, and so on. And then, of course, you can measure also what is the real efficiency. And you see that it's 36, 30, 16, so quite a lot less. And now you would say, well, okay, it's obvious the engineers are more good and they just didn't do this very well. But actually, engineers are really, really very good. So they build something that is actually working reasonably, I mean, close to what you can do. They optimize this over long times. And now you can wonder, well, then what is the reason for this discrepancy? And of course, one cannot track it down exactly in these complicated machines, but what various people have done, the first ones were Novikov and then Chambardal in the 50s. But then in a nice piece in American Journal of Physics, Curzon and Alborn discussed this a bit. And they were actually motivated by some lecture course that they were giving. And they said, well, okay, the real engine, it has volume, has surface, and it takes a while that the heat actually goes, through all these structures. There's a finite heat capacity, heat conductivity. And therefore, I mean, there will be a constant, so the heat that is transported per unit time will be a constant times the temperature difference. So it takes a while until everything thermalizes. And so when you take this into account, then you get completely different answers now.
Never come out the connection.
The efficiency. In fact,
The connection of here
you
never
now
come
go
out. Any
and you work
notification
out
for this
what
one.
is
Plug
the
in, come out
efficiency
the
at
notification.
maximum power.
So this is not
of the
no
engine. You get this kind of
this is not
answer.
recognized.
No, it's
Which is
nice.
not
Because when you plug in, they will
efficiency. And
came out
the
with
nice thing is
notification.
that when you go now and you take the table and
So you have like this shape?
I put in the
So you want me to
middle one, label
change it?
this
Change it
equation
to-
here, and you work it out, and then you see that this actually comes much closer to the efficiency of these engines. So it is therefore some of the deficit that these engines had were to do with the fact that they were really at running and finite.
Because when you plug in, they will come out the notification.
Okay.
But there's no
So finite power finite power engines are not as efficient as a quasi-static engine. So that's fine, that's all classical. And so we were wanted to look a little bit, or many people have been looking into the question, okay, how is this all panning out when you have really a nanoscale, a quantum mechanical, a quantum heat engine? So let's say a two-level system, and then you couple this to the environments. And of course, there's a big difference now. So for example, these things are all surface and no volume. So you can imagine already that maybe these constraints that personal one put in might not apply quite so much. You can more easily imagine that you can also make the thermalization, for example, very much more rapid. So, well, okay, so we want to look at a particular engine here. This was not important, but for various practical reasons, we looked at the Otto engine. And so you have your thermalization step, you have a compression step, another thermalization step, and an expansion step, and you will run this periodically. And so, of course, what you want to do, I mean, if you want to have this, if you want this machine to run very fast, then you will have to make the thermalization fast, and you have to make the compression and expansion steps very fast. And then the question is, well, can you do that? And what happens if you do it? Okay, so what will happen? Okay, so you have here, I mean, here it's just you put them in thermal contact, that's relatively easy. The adiabatic expansion, you have to put in some control field that typically changes the eigenvectors of the system. And so you have to follow basically the change of the eigenvectors. And so you can already imagine when you do this too fast, then adiabaticity fails and you might start to get into problems. So let's discuss these two things. And so again, I mean, this is not resource theory. So I use typical definition of work that, for example, from Malitsky, where the work is the expectation value of the rate of change of the Hamiltonian integrated over time, and the heat is the rate of change of the exit voltage. So one can argue about this, but let's say I use this here for this discussion. Okay, so first thing, so we have here our thermalization steps, and clearly what we want is we want them to be fast. So we want to couple the system very, very strongly to the environment, and eventually infinitely strong. Yeah. So and then you really have to start to worry, because if you couple the system now to the bath of this heat bath to your tiny heat engine very strongly, you may actually affect the eigenstates, but in particular, you should really work out how much work does it cost you to actually couple and decouple the heat engine from the bath. Yeah? And so now this is a highly non-trivial issue. There's plenty of papers about this. And in many cases, this really costs you a lot of work potentially. And this work typically will grow with the coupling strength that you are applying. So therefore, I mean, this is something that you have to take into account. And so that's certainly what we did. And we do this by looking at a really proper environment. So really a spectral density of harmonic oscillators that are coupled in some particular way to the system. And let me ask the question, is there a decoupling cost? Yes or I should say that the decoupling cost the work is, of course, well, the change of the coupling Hamiltonian integrated over the time it takes you to switch this thing on. Okay, so, and the answer will be no, there's no decoupling cost when you do it right. This is not entirely obvious from a mathematical point of view, I mean, but you can work it out, of course. But I want to give you a sort of a physical argument why you expect this at least. And so here, for that, we use a particular method for modeling system environment interaction. And there's a small trick that is used, actually, we introduced this for numerical reasons, but it's actually very helpful also in these kind of studies. So normally you would say we have a system, we have our environment made up of harmonic oscillators. Each harmonic oscillator couples to your system. There's a frequency distribution. And then you have a dynamics, and then the typical argument is that, well, yeah, this becomes irreversible at some point because all these different oscillators have different phases, and you have some random phase dephasing, and eventually stuff goes into the environment but doesn't come back again. And I never found this very, well, it's convincing, but I mean, it's not very intuitive. But the nice thing is what you can do is you can take actually this harmonic oscillator path, which is a bunch of free harmonic oscillators coupled linearly to your system, and you can make a mode transformation. And you can do it in such a way that you map this continuum of harmonic oscillators onto a discrete but infinitely long chain of harmonic oscillators with nearest neighbor couplings only. Okay, so that's not obvious. I could show you the proof, but this is uses the fact that, I mean, you use theory of orthogonal polynomials for that. That's very easy. Okay, so in the end, this and that is exactly the same. So this is a proper unitary transformation. There's mode transformation. There's no difference. Physics stays completely. I mean, let's say certainly on the level of the system stays completely the same. And even here, take a measurement here. You can translate it to a corresponding measurement here. So it's, no physics has changed. Okay, so chain nearest neighbor interactions. The next observation that you make is when you make this transformation, so it's an exact transformation, and you can actually work it out analytically often. And what you find typically is that now the coupling constants in this chain, at the beginning, they are sort of, a little bit disordered. And then they sort of converge to a constant. And the on-site energies do something similar, and then they converge to a constant. And you can observe this initially numerically, but it turns out that you can prove that. So when the spectral density has a certain property, namely that it's basically called a Shego class. That means that when it's integrated, when you integrate the logarithm of it over 1 minus x squared from minus up to 1, then this should be minus, that should be not minus infinite. Well, okay, that's not intuitive, and I have no idea really where this is coming from, but you can use this to actually prove this. Every spectral density that satisfies this condition, when you make this mode transformation, you have this property. And so that means actually that the chain is at the beginning sort of non-trivial, so something interesting might happen, but then it becomes completely like a translation invariant chain. So every excitation that reaches that part will just wander off to infinity. And so here you see much nicer already how you get sort of equilibrium, because any perturbation that you introduce at the beginning by coupling the system to the environment will propagate away to infinity. And then locally, it settles again to the initial state, basically. So that's the intuition, and you can show this. But here, I mean, okay, I want to, instead of showing you the proof, I want to show you numerics that indicates that this is really the case. So here you have the system, and the equilibrium, thermal equilibrium energy in this case would be 2. And initially it starts at the ground state, and you see, well, it thermalizes nicely. You can also see that when you work out the matrix element for the coupling between the system and the environment, which will be the relevant one for determining the coupling work, that actually, this is a logarithmic scale that goes exponentially to 0. So this is the absolute value level. So this goes exponentially to 0. So therefore, if at the end of this process you will actually decouple, you will find that the decoupling energy is that you need for that is 0. And you can also see what happens in the chain. Well, this is some later oscillator, I mean, in the environment. And you see initially it feels nothing, but the system has been coupled, then it feels something, and then it stops feeling it because the excitation passes through that oscillator and goes into infinity. That's kind of a nice, I find also satisfying picture. And it's also quite helpful when you want to prove things. Okay, so that should convince you without seeing the actual proof that the decoupling work can be made very effectively, very, very small, because the matrix element decays this exponentially in time. So you just have to wait a little moment, and then it can be made very small. So this, you can imagine, can really be bounded, and you can run the engine faster and faster if you have the right properties. So that's nice. So that's the first step. So, and I should say, I mean, that's very important. This is true when the coupling is like that. If you have counter-rotating terms in the coupling, this statement is wrong. Then actually, you can wait as long as you like. This expectation value here will actually never drop to 0. Well, I mean, it will oscillate sometimes through 0, but I mean, it will not go to 0. So this is really important, which kind of interaction you are using. Okay, so thermalization is sorted now. Now we have the part that actually motivated me to look at this in the first place, and that is the fact that we have the expansion and compression strokes. And of course, we also want to make those very fast. Now, in those strokes, the eigenvectors of the systems are changing in time. And the faster you are making this change, the less well, I mean, the system can follow this change, and you're basically breaking adiabaticity condition. And so what will happen is that you will create coherencies and eventually also transitions, which lead effectively to an additional dissipation, and this will lead to friction basically, and this runs under the title of quantum friction. And so then, it's already Ronnie Kozlov in 2006, he sort of said, well, okay, this is no problem whatsoever. We just put in a lot of dephasing in the instantaneous eigenbasis, therefore we actually prevent these coherencies from being built up. And if we want to run the machine faster, or at least this compression stroke, we just increase the dephasing strength. And then we can run the machine as fast as we like. So that's that looks tempting. And when you put this in, I mean, it's no problem. You write the master equation for the dephasing noise, and you see that it works. But of course, the problem is really, have I been cheating here? Yes or no? I mean, this is now actually in reality coupling another heat path to your engine. And you really have to have a look now whether this engine will now, you know, what kind of work it does in the heat bath, how much heat is flowing in and out, and whether this, whether this maybe actually negates all the benefits from introducing the dephasing, whether this is so costly that in the end the efficiency goes down. And so initially, I mean, I thought, okay, you know, from classical thermodynamics, we have this nice Gaussian-Albert bound. For sure, there's an extra cost here. And so we started the analysis to show this. Well, okay, so now we have these methods for treating our environments. So we can put in here an exact environment, really use also numerical methods if we want to analyze it. But it turned, I mean, we started with this to just gain some intuition, but it's really painful. So the simulations take very long. And so we used another observation that we knew from developing all these numerical methods. You can take here such an environment, and you can remember that actually here the distant parts of the chain, they are, I mean, the couplings are, you know, translation invariant, the energies are translation invariant. This is really basically only there for transporting away excitations. So you can try and see whether you can actually have an initial one or few oscillators, and then you put a lint blood bath here. And then you, of course, you have to ask yourself whether you are changing anything on the system. And if you do these things right, then you can actually prove that having this harmonic chain infinitely long, or having this system here gives exactly the same answer on the level of the system. So all the system observables will be the same, and that will be the case when the two-point correlators of this environment and the environment that is represented by a chain are the same. When you start in a thermal state, and of course your Hamiltonian has to be a Hamiltonian, this just quadratic, and then you can this section. And so that's of course a nice simplification. It's also a very good simplification for analytical work because you don't have to treat with an infinite chain of systems anymore. But of course, you have to be sure that you will not, make some small error that might grow when you increase the coupling strength from the system to this first, of course. So that's an important point here. And so this is, this is not a miracle. This is known in communities. So it's pseudo mode picture, so it's fine. So you just have to make sure that really, in this case, you have not introduced any undue approximation or swept some thermodynamic cost on the carpet. And so that works. And then a nice outcome of this transformation is that this system here, in the limit when the coupling to this Lindblad bath here, this little gamma, is much, much larger than this capital gamma, then on the system level, that will introduce an effective dephasing, which has a strength that is roughly like that. So that is a temperature-dependent term, so temperature of this environment, and then some Lorentzian. So that you can also show. So you have now a dephasing that you can tune in various ways. You can either increase the coupling between the system and this harmonic oscillator. You can adjust the damping here, or you adjust the temperature. And so we did both, but in the end we adjusted the temperature because that's the best thing that you can actually do. And so now one can use this, and one can first start and play a little bit, and one can do some numerics. Sorry. I should have said, okay. So let's go back here. So here with this system, we have really an explicit representation of the environment. We can look at the energies of all the harmonic oscillators there. We can really measure exactly the energy that goes into that system. Yeah. Now, of course, in this new effective picture, we have to think a little bit harder, and we have to work out how we can actually really measure the energy that goes into this harmonic oscillator and this Lindblad environment, and see that whether it's really the same as the proper picture. And you can do this. So you can work out. So you have some coupling Hamiltonian. You have some energies that are defined here by the propagator according with the Lindblad generated by the Lindblad operator of this total environment here. And so there's an analytical derivation for that, and you can work this out, and you can also check that it's really the same. So this is a numerical comparison of both pictures, and the same. That's not a proof. There's a real proof for it, but numerics is always nice to see. So you can work out, therefore, in this effective environment picture, you can work out what is the heat flows, what is work that is being done here, and all these things. So you can really make a thermodynamic analysis now of the cost of this dephasing environment that you enter the system. And when you do that, then you see, okay, here's the red dashed curve is basically an analysis where you ignore any cost associated with the dephasing environment. You just look at the system. And the blue solid curve is when you take also really properly all the workflows and the heat flows with the dephasing environment into account. And sometimes actually this can indeed lead to a slightly higher work output, because now we have this extra coupling term to the dephasing environment. This is time dependent because the system, we have to follow the eigenbasis. And so there might be some extra work involved. But what you see is when you increase dephasing, actually the power of the machines grow. So that's great. So that's what we expected. We increase the dephasing, we destroy the coherencies, we destroy this quantum friction, we can run the machine faster, and therefore we get more power out. But now you see a big difference. If you ignore the dephasing path, then the efficiency seems to be staying at essentially the maximum. If you take into account all the costs involved with the dephasing path in this particular example, then you see that the efficiency just goes down very steeply. And so at that point, we thought, okay, this is exactly what we were expecting. I mean, there's an extra cost, and therefore, I mean, in the end, probably it can only be sort of the efficiency of the personal warm up or something like that. Of course, this was just one numerical example of one particular environment. And so then you start to use all the insights that you gain from these numerics to in the end produce an analytical calculation of the heat, the extra heat that is dissipated into this thermal, into this dissipative, decohering environment. And again, I'm not going to show you the derivation, it's in the paper, but you can bound it from below and from above. And it will depend on, well, how strongly you are coupling the system to this external oscillator. It will depend on the damping rate of that oscillator, on the central frequency, on various properties, also on the coupling between the system and the heat path and various parameters. So that's great. So that's an upper bound. And of course, well, now we want to have a look whether we can actually make this small. And of course, you could say, well, okay, no problems, make this capital gamma 0 and everything is fine, but then I don't have any dephasing. So then something that is not in the range of validity of the derivation of this object here. And so one has to have a look a little bit more closely. So we have here our effective phasing rate that we get from this dephasing environment. So that was this Lorentzian function, and the function that depends on temperature. So actually, when you increase the temperature of the dephasing path, the dephasing grows. So that's the handle that we want to turn it now. And we also see that this function here is more or less appearing here. So it's clear that we can somehow replace this, and we can use this expression here to eliminate some of the parameters here. So then what you want to do is, you want to keep all sorts of things fixed, because you need only one example where this quantity can be made arbitrarily small. And so you take the peak location, omega naught, you fix it. The width of the dephasing path, the little gamma, you fix it. You take the effective dephasing rate, so that's the dephasing that the engine sees, and you fix it. And you take the thermalization rates, which is basically gamma times NH, which is the thermal Monod number, and you fix it. And so when you can fix all these things, and then the only thing that you really change now is the temperature. And what you then see is that this extra heat flow can be made out. So there is a regime in which you can make actually this thermodynamic cost of attaching the dephasing heat path. You can make this basically 0. Okay. Initially, I mean, this is not a completely trivial endeavor. So initially, we actually tried to do this differently. We have put a 0 temperature path, which is much nicer to solve analytically. But then, when you try and do this, you actually run into the problem that you go to a spectral density that is non-physical. So basically, the width is as large as the central frequency, and that is not a physical spectral density. So here, this defect doesn't happen. So this is a perfectly acceptable environment that achieves that. So that's nice. So now, I mean, we come to the conclusion that yes, typically attaching a dephasing path costs you something, and therefore it reduces the efficiency of the heat engine. But if you do it cleverly, then for any fixed power, you can actually make this cost arbitrarily small. So that means you can grow the power for each choice of that power, you make the cost small, and therefore you can run this machine now with the help of dephasing at arbitrary speed with an efficiency that is actually as close as you like to that of the quasi-static. So that's kind of nice. Now, now we have to talk a little bit about potential caveats. Yeah. So let's okay. So that's the positive one. So yeah, that's great. However, there's one thing that in our analysis we have not actually studied carefully, and that is that of course when you have to couple and decouple your environments, and you have to keep your timing, so you need a clock. And so you have to also take into account whether this clock might have a undue thermodynamical cost, especially when you want to run the machine very, very fast. And so as I said, we have not done this properly, but at least in this paper here, if the clock is very high dimensional, then it will actually become this use of the clock should be with negligible cost, but we have not shown this properly. We have to analyze this. This is also interesting because what this could mean is that there might not be, so it might, for example, be that also that we can reduce this cost by making the clock a little bit fuzzy and imprecise. And that would actually mean that the machine would now, in every cycle, the cycle would not have exactly the same length. You switch on and off the environments at different times. So actually what would happen is that the power on would fluctuate. And so that's interesting in the sense that so there are works like Pizonka and Seifert for classical heat engines under certain assumptions, where they show that if you want to have a machine that works arbitrarily fast and under high efficiency, then it has to fluctuate a lot. So it may be coming out like this here. But really what I would much have preferred to do is, instead of using the Jalitzky definitions of work and power and so on, I would much rather have done the same analysis using resource theories. It's just that I don't exactly know how to do this because I really have to talk about this dephasing environment. There's dynamics involved, and now really finite time dynamics. So somehow we have to put d by dt into the resource theories. And well, certainly I didn't know how to do it. So maybe someone here feels motivated by this to actually take this setting and really prove this, I would say, properly using resource theories. And so with that, in word of encouragement.
Thank you, Martin. We have time for one or two questions.
Maybe around 5 years ago, I and my co-author showed that both for the classical Markov system and quantum Lindbladian system, the efficiency and power must have a trade-off. And current efficiency implies the zero power. Is there so what is the relation between your results and this type of result? And many others also show this type of result. My results that the trade-off relation between the power and the efficiency, and if we increase the power, then the maximum efficiency decreases. This type of trade-off relation is derived in non-equilibrium statistical mechanics, and I derived one of them for quantum.
Okay, so I'm not entirely sure, of course, what assumptions this was made, but here, of course, we have not just a heat engine. I mean, with one heat bath and with one hot bath and one cold bath, but we have effectively a system with 3 heat baths. And so I'm not sure whether this be included in your analysis, because if we would not have this dephasing bath, then I would completely agree. I run the machine faster, the efficiency goes down, no doubt about that. But here we have a slightly different situation. So I would have to look at it carefully whether your theorems really should apply or not.
Debating bath must be very important.
Yeah, absolutely. That is absolutely essential. I mean, without the dephasing bath, this just fails, and it's completely clear that you run the machine faster, efficiency goes down.
Thanks for the nice talk. I was wondering if, with respect to the point you mentioned about the timing resources, including a clock, do you think there's a way of making this this engine along with its dephasing step autonomous? There's some autonomous model for that.
Well, that would be exactly the point, that we would attach to it some device that basically autonomously switches on and off the couplings to the environments. So I think it might be possible, but I'm not absolutely 100% sure is what it will do to the efficiency of the engine. Yeah. So I think this is absolutely an open question, so we don't know.
So should I think of this dephasing bath as an actual bath, which is put into thermal contact with the engine? And then if that's the case, why doesn't it exchange heats with the...
Oh, it does. That's the point. I mean, so this dephasing bath is in touch with the machine. And in fact, it's, in this case here, we leave it on all the time. And then we switch, in addition, the hot and cold heat bath, well, to contact those on and off. And so indeed, what you see is actually there is heat transfer between the dephasing bath and these other hot and cold baths. And this actually is an extra cost that has to be taken into account. And that comes out of this analysis. Yeah. So there is, yes, there are extra heat flows, and you have to take account of this.
So why doesn't it change the overall efficiency then?
Well, I mean, if for a given amount of work you transfer more heat, let's say from some environment to the cold environment, you would the efficiency of the engine will change. I mean, you have to take into account all the heat flows and all the works that you have, and then you have to take the ratio, and then you have to about what it is. And so, if you have here, for example, an additional bath, you don't take any work out of it, but you have a heat flow into it or out of it that will affect the overall efficiency, thermodynamic efficiency.
And can it be the same temperature? Can the dephasing bath, I can consider it to be the same temperature, make it be the same temperature as one of the baths that I'm using as a...
You're not in our example. We have to make it actually really hot. So in this the way in which we managed to increase the effect, I mean, let's say to increase the effective dephasing rate, was increasing the temperature of the dephasing bath. So this is actually a high temperature resource that we addition to the system.
And then if I were to instead run my heat engine between the dephasing bath and the cold bath, I get it to, like, is that something you could have done instead of doing it in the other two baths? Or?
If all the three baths are connected to the system, to the system.
Maybe there's an opportunity here to also discuss this further over coffee and on to the next speaker in the interest of time, but let's thank Martin again.